Welcome to the second lecture of module 4 of mass transfer operation. In this module we are discussing absorption, and in the last class or in the last lecture we have discussed mainly introduction on absorption process. We have also discussed the selection of different solvents for absorption. And third thing, we have considered how to determine the minimum liquid flow rate for absorption. So, minimum liquid flow rate. So, in this lecture we will consider primarily on the design of packed towers, and in this we will consider first method based on the individual mass transfer coefficient. So, mostly we will concentrate in this lecture individual mass transfer coefficient method. The conventional equipment for carrying out gas absorption operation is the packed towers and the plate towers that we have already discussed. And we have seen that in plate column the gas and the liquid phases come in contact with discrete stages. So, it is called stage wise contact. That means, if the gas flows co-current or counter currently in the column, the liquid flows from the top through different trays and exit at the bottom, and then gas enters at the bottom and it exit at the top. So, if so happen, then the gas generally in a plate columns goes through the perforation of the plate and it passes through the liquid pool. So, the mass transfer happens when the gas and liquid come in contact in the stages with respect to the liquid pool available on each stage. So, the transfer happens only when there is a liquid pool, and in the empty space between the trays where there is no liquid present, there will not be any mass transfer. So, again the mass transfer will happen to the next stage when there will be gas and liquid contact. So, that is why in a plate column the contact of the gas and liquid is discrete, and hence it is called stage wise contact, and the gas and liquid concentration undergo step change from one plate to the next plate. Whereas, in case of packed column, the liquid flowing down through the packing remains in contact with the upflowing gas at every point of the packed section. So, as you know, in packed section the packing are no random or in a structured way, it is packed inside a column. So, when the liquid flows, it flows onto the surface of the packing material and it is continuous from top to bottom, and the gas also passes through the available space between the packing materials. So, at every stage of the column there is intimate contact between gas and liquid. So, that is why this type of packed column is called as continuous differential contact equipment. So, there is no step change. So, every no point there is a change of concentration as the gas flows from bottom to top or liquid flows from top to bottom. Now, the sizing of a packed column basically includes the few stage which we need to consider. First is the selection of the solvent, and second is selection of packing, then determination of the minimum and actual solvent rate, determination of the column diameter, determination of packed height, and the design of the liquid distributor and redistributor if necessary, packing support and the gas distributor, design of cells, nozzles, column support, including selection of the materials to be used for the tower internals and to build the tower. So, among this the sizing of the packed towers, the selection of the solvent already we have discussed in our last lecture. Then selection of packing material, different type of packing material we have already discussed, but in detail design of the packing material you will learn in your design course, but it is mostly to enhance the interfacial area, reduce the pressure drop inside the column. So, based on that we need to select the packing material. Then determination of the minimum liquid rate or the solvent rate and then actual solvent rate. So, that we have already discussed in the last class. Determination of the column diameter also we have discussed to some extent during the discussion of our equipment. Now, in this lecture we will primarily concentrate on the determination of the packing height. The first 4 steps, that is selection of the solvents, have already been discussed in previous lecture in absorption lecture 1. In these sections we shall concentrate upon the determination of the height of packing required for a particular separation. The discussion will be confined to the case transfer of a single solute. Mostly we will consider the single solute transfer and how height of the packed tower is required, that we need to calculate. The following items and variables should be known or available for design purpose. What are those parameters or variables? That is, equilibrium data should be available with us. The flow rate and the terminal concentrations of the gas and liquid phases, that should be available. Individual or overall volumetric mass transfer coefficients, sometimes called capacity coefficients, and which is based on the gas phase and liquid phase. We should have those data available with us, that is KYA, small kya, small kxa and capital Kga and capital Kla, capital Kya, etc. These are the parameters for that particular systems we need to, or the mass transfer coefficient, either individual or overall mass transfer coefficient should be available for finding out the packed tower design, that is the height of the tower. We will concentrate first design based on individual mass transfer coefficient. Consider the packed tower which is shown over here. The gas and liquid phase contact are in mole fractions unit, that is small x and small y. So, the flow rate G and L are taken on the basis of the unit cross sectional area, that is mole per unit time per unit area. So, for unit cross sectional area L1, L2, G1, G2 and G and L, these are the gas and liquid flows. The specific interfacial area of contact between the gas and the liquid, which is small a, is taken on the basis of the unit packed volume and has the unit of either meter square per meter cube or feet square per feet cube. So, per unit volume of the packing. Now, if we consider a steady state mass balance over a small section of the column of thickness dz, which is shown over here, small thickness dz. So, the steady state mass balance would be the rate of flow of the solute with the carrier gas would be G into Y mole per time into area, G into Y. So, which is the gas flow rate or the solute gas flow rate. The change in the solute flow rate in this section would be d G Y. This is intrinsically negative in case of absorption, because the solute transfer from the gas phase to the liquid phase. So, since the solute concentration is decreasing as the gas flows from one location to the other location. So, it is intrinsically negative. Now, let Na be the local flux and small ky be the individual gas phase mass transfer coefficient. So, small ky and Na is the local flux. Then the packed volume in the differential section for unit cross sectional area, if we consider. So, the packed volume of the bed we can get 1 into dz. So, that is the packed volume. Now, the interfacial area of contact in the differential section is A into 1 into dz. So, this is the interfacial area of contact. Now, the rate of mass transfer of the solute would be A dz into Na. So, that is the rate of solute transfer or mass transfer of the solute. Now, we know the packed volume, we know the interfacial area of contact and also the rate of mass transfer. So, a mass balance over the elementary section of the bed which will yield A into dz into Na would be equal to minus d gy, which is equal to minus g dy minus y dg. So, since the carrier gas is not soluble, the change in the total gas flow rate is also equal to the rate of mass transfer of the solute. So, we can write minus dg would be equal to A dz into Na. If we rearrange and putting Na is equal to ky into y minus yi, y is the concentration in the bulk and yi is the interfacial concentration between the gas and liquids. So, flux Na would be ky y minus yi. So, we can write A dz into Na 1 minus y would be equal to minus g dy. If we rearrange, dz would be minus g dy divided by kya into 1 minus y into y minus yi. Now, if we just integrate within the appropriate limit, we get z would be equal to integral 0 to z dz would be equal to integral y1 to y2 minus g dy divided by kya into 1 minus y into y minus yi. Now, if just change the limit from y2 to y1, so this negative sign will be absorbed. So, we will have integral y2 to y1 g dy divided by kya 1 minus y into y minus yi. The evaluation of the integral which is given over here for the height of the packing requires the calculation of yi. So, that is the interfacial concentration. So, the integration is not straightforward since the interfacial concentration yi is not explicitly known as the function of the variables. Since yi is not known, this integration is not so straightforward. So, we have to find out ways to find out the interfacial concentration. Now, the following general steps should be followed to calculate that. First, we need to draw the equilibrium curve on the xy plane for the particular gas liquid systems, and then draw the operating line from the material balance equation. So, we have material balance equation. So, we can get the operating line equation here. So, Gs into y by 1 minus y minus y2 by 1 minus y would be equal to Ls into x by 1 minus x minus x2 by 1 minus x2, and here small y capital Y as we have already discussed. this is the relation. If the liquid mass flow rate, that is the rate of flow per unit cross sectional area, is given as L and which is known, in that case the minimum liquid rate on the solute free basis L min is to be determined following the procedure detailed earlier. That means, now if L is known, that is fine, if it is not known, then we have to find out the pinch point through the slope of the operating line, and we have to calculate the minimum liquid flow rates, and then we have to use the actual liquid flow rate should be taken as the suitable multiples, which will vary between 1.5 to 2 times of the minimum rate. So, if we do not have data for the liquid flow rate, we have to know the slope of the operating line and we have to calculate from the pinch point the minimum liquid rate, and then we can calculate the actual liquid rate. The outlet liquid concentration x1 is obtained from the overall material balance. So, this is the procedure we have to follow. Then take any point x y on the operating line. So, at any point, if we take, see figure over here, we can take any point x y over here. Using the known values of kx and ky or kxa and kya, we can calculate the slope of the operating line from the point OX to meet the equilibrium curve at point xi yi. Yi is known for the particular values of y. The line OP over here, you can see line OP is called the tie line. So, which will give the interfacial concentration xi and yi. Now, we have to repeat the steps for a number of other points on the operating line. If kx and ky or their ratio are constant, a set of lines parallel to the one drawn in step 3 may be constructed. So, if this is the straight line, then we can parallel line we can draw in multiple points, and we can get the multiple data for a set of x and y, we can get a set of xi and yi. Please note that very often the mass transfer coefficient combined with the specific interfacial area, that is kxa and kya, rather than kx and ky are given or known, because sometimes the total interfacial area may not be available. So, it is given in terms of kxa and kya. Now, we have set of yi pair for y2 less than equal to y and which is less than equal to y1. So, with this limit we have a set of y and yi pair. So, from the tie line we can obtain for a particular system. Now, we can calculate g is equal to gs 1 plus y at each point. Note that gs can be calculated from the given feed gas flow rate. Now, calculate the values of the integrand for a set of suitably spaced values of y, then evaluate the integral for the equation graphically or numerically, and this procedure will be illustrated later in an example. So, we will see how to calculate that. The height of the packing then can be determined using the other type of individual mass transfer coefficient. It may be kx, kg, kl, capital Ky, capital Kx and so on. The design equation given below can be derived following the above procedure. So, this is the design equation, integral x2 to x1 minus L into dx divided by kxa into 1 minus x into xi minus x, which would be equal to integral y2 to y1 g dy divided by kga pt total pressure into 1 minus y into y minus yi, or it can be in terms of the liquid average concentration. We can write integral x2 to x1 minus L dx divided by KLA CAV, that is average concentration, into 1 minus x into xi minus x. So, this way we can calculate the height of the tower. The height of packing for a stripping column can be obtained in a similar way, but here y2 should be greater than y1 and the gas phase driving force at any point is yi minus y. So, the design equations will change to z is equal to integral y1 to y2 g dy divided by kya 1 minus y into yi minus y. So, almost similar procedure will be followed in case design of the packing for the stripping column. Now, let us take an example how to calculate the tower height using KYA. A packed tower is to be designed to absorb 95% of sulfur dioxide from an air sulfur dioxide mixture using pure water. The entering feed gas mixture contains 15 mole percent sulfur dioxide and 85 mole percent air at 303 Kelvin and 101.3 kilopascal total pressure. The feed gas rate is given, which is 1000 kg per hour. The solvent rate is also given, which is 30,000 kg per hour. The tower cross sectional area is 1 meter square and the data which are given Kxa, which is 1.1 kilomole per meter cube second, and Kya is 0.07 kilomole per meter cube second. Now, we have to calculate height of the tower using Kya. The data which are provided are the equilibrium data, which is x and y. So, now for this sketch, the same sketch we can use over here, and we need to calculate the average molecular weight of the feed gas. Average molecular weight of feed gas, which is equal to, we have 15 mole percent of sulfur dioxide. So, 0.15 multiplied by its molecular weight is 64 plus we have 85% air. So, 0.85 into the molecular weight of air is 29, and so it will give 34.25. Now, we need to calculate the feed gas rate. And this is given as 1000 kg per hour. Now, if we convert to kilomole per hour, so this should be equal to 1000 divided by the average molecular weight is 34.25 would be kilomole per hour, and which is about 29.2 kmol per hour. So, this is basically G1, so which is entering feed gas. Now, feed concentration, which is Y1, is given as 15% 0.15. So, if we wanted to calculate in mole ratio unit, so it is capital Y1 would be equal to small y1 divided by 1 minus y1, which is equal to 0.15 divided by 1 minus 0.15 and this would be about 0.177. This is mole ratio unit. Now, we need to calculate the feed gas rate on solute free basis. So, feed gas rate on solute free basis this should be basically G s, which is equal to G 1 into 1 minus y 1. So, G 1 is 29.2 into 1 minus 0.15, that is 15% no feed gas concentration. So, it would be equal to 24.82 kilomole per hour. Now, the SO2 which is entering into the tower is equal to G 1 y 1. Now, if we substitute the values, G 1 is 29.2 and y 1 is 0.15, 15%. So, it is 4.38 kilomole per hour. Now, as per the problem given is in the packed tower, we have to absorb 95% of the SO2 from air sulfur dioxide mixture. So, 90% of G 1 y 1, 95% of G 1 y 1 to be absorbed. So, SO2 absorbed would be equal to 4.38 into 0.95. So, this is about 4.16 kmol per hour. So, the SO2 which would be leaving, the total SO2 which is entering and then which is absorbed, the difference between these two would be the leaving one. So, this is equal to 4.38 minus 4.16 kilomole per hour, which is equal to 0.22 kilomole per hour. So, now we can calculate capital Y 2 would be equal to 0.22 divided by G s, which is equal to 0.22 divided by 24.82. So, this would be about 0.0887. So, we can calculate in mole fraction unit, small y 2 would be equal to capital Y 2 divided by 1 plus capital Y 2. So, which is equal to 0.0887 divided by 1 plus 0.0887, which would be equal to 0.0088. So, this is mole fraction of the exit stream or the SO2 leaving column. Now, we need to calculate the exit stream concentration x1, the liquid phase concentration. To do that, we know the material balance equation, that is Gs into y1 by 1 minus y1 minus y2 by 1 minus y2 would be equal to Ls into x1 divided by 1 minus x1 minus x2 divided by 1 minus x2. So, Gs we know, which is we have calculated 24.82 kilomole per hour. Ls which is given is 30,000 kg per hour, which is pure water is used as solvent. So, it will be 30,000 divided by 18 kilomole per hour. So, this is essentially 1666.67 kilomole per hour. Y1 which is the entering feed gas, each mole fraction is 0.15 and Y2 is 0.088 and also it is given that the feed which is coming feed liquid solvent is free of sulfur dioxide. So, x2 would be 0. Now, if we substitute all these values in these equations, so putting these values, x1 is equal to 0.00249. This is the concentration of sulfur dioxide in the exit stream of liquid. So, now we have the equilibrium data. So, we can plot the equilibrium line and with the data we have obtained, that is x1 and y1 and x2 and y2. With this data data set we can plot the operating line. So, we know the all the points and we can just join the terminal points. So, then we can obtain the operating line curve. Now, equilibrium curve and operating line curve are known to us. We have to draw the tie line. So, to draw the tie line, we need to find out the slope of the tie line. Slope of the tie line is we have defined is equal to minus k x a divided by k y a. So, these values are given. K x a is 1.1 kilomole per meter cube second. So, 1.1 divided by 0.07. So, which is equal to minus 15.71. So, with this say you consider a point somewhere at P which is x I y I and with this slope you can draw the tie line. So, this is point say O with x and y. So, with no different if these are parallel straight line with this slope, we can draw the several tie line with parallel to this one with this slope. So, from this we will have a sets of x, y and x I, y I. Once these data are known, we can just calculate the y I values and y values, and we can calculate 1 minus y, then y minus y I, and then 1 minus y into y minus y I, and then 1 by 1 minus y into y minus y I. So, these values we can calculate. Once we know these values, this table we can generate with the tie line values. Now, we can plot with the equation we know for the calculating the height of the tower is z is equal to integral y2 to y1 g dy divided by k y a into 1 minus y into 1 minus y I. So, g by k y a integral y2 to y1 dy by 1 minus y into 1 minus y I. Now, if we plot here in this figure, this is y axis and this is x axis. X axis is y and y axis is 1 by 1 minus y into 1 minus y I. So, if we plot with the data with the limit we have for x1, y1 and x2, y2, we can get this graph, and then we can calculate the area under the curve. So, if you do any method, if you apply to find out the area under the curve, many methods you have learned, the trapezoidal rule, Simpson's 1/3 rule, Simpson's 5/5 rules. So, there are different rules available to calculate the area under the curve. You can use either one of them and see looking into the pattern of the plot. So, you can calculate the area under the curve, which would be typically if you calculate for this, it would be 16.5. So, we know the values of this integral. We have to calculate g, we will take the average values of g because it is changing because of the solute transfer. So, we will consider here the average values of g, k y a is given. So, we can calculate the height of the tower. So, k y a over here, k y a is 0.07 k mole per meter cube second. So, this we can just multiply with 3600 kilomole per meter cube hour. In this equation, Z is equal to G by K y a integral y2 to y1 dy divided by 1 minus y into 1 minus y I. We need to calculate G. So, G 1 dash would be G 1 divided by area, which is 29.2 divided by 1 meter square, which is 29.2 kilomole per meter square hour, and G 2 dash would be equal to G s by 1 minus y 2 into 1 meter square, which is equal to 25.04 kilomole per meter square hour. Okay. So, now G 1 and G 2 we have, G 2 dash we have calculated, and we will take the average of these two. So, G should be equal to G 1 plus G 2 dash, G 1 dash by G 2 dash by 2, and if we substitute that, it will be 27.12 kilomole per meter square hour. So, KYA is 0.07 into 3600 kilomole per meter cube hour. Area under the curve, that is integral y 2 to y 1 dy 1 minus y into y minus y 1. So, which is equal to 16.5. So, we can calculate Z by putting the values of G dash 27.12 divided by 0.07 into 3600 into 16.5 meter. So, if we calculate, this would be about 1.78 meter. So, this is the height of packing required for this particular problem. So, we have seen how to design based on the individual mass transfer coefficient method, and we calculated the height of packing required for a given separation, considering different parameters to calculate the interfacial concentration, how to obtain tie line, and then how to plot it, how to get the sets of data to plot the area under the curve, and we obtain finally the height of the packing. We have discussed in detail. Thank you for attending this lecture, and we will continue our design of packed towers with different other methods to find out the height of the packing.